Hello, it's Mitali Kumawat from Group 319 and here I am presenting my topic Ionic channels. Ionic channels. Ionic channels are integrated membrane proteins that facilitate the movement of ions across cell membrane. They play a crucial role in various physiological processes including nerve impulse transmission, muscles contraction and maintaining the resting membrane protein of cells. Potential of cells. Ionic channels can be classified based on their gating mechanisms, which determine when the channels open or close. The main types include voltage gated channels, liquid gated channels, mechanically gated channels, linked channels. So first we will discuss about voltage gated channels. In the voltage gated channels, these channels open or close in response to changes in membrane potential. For example, the sodium and potassium channels are essential for action potential in neurons. Second one is ligand-gated channels. In ligand-gated channels, these channels opens in response to the binding of specific molecules such as neurotransmitters. An example is the nicotinic acetylcholine receptor, which opens in response to acetylcholine binding. Next one is mechanically gated channels. In mechanically gated channels, the channels respond to mechanical forces such as stretch or pressure. They are important in sensory cells like those in the skin or inner ear. Fourth one is lag channels. In the lag channels, these channels are always open and allow ion to passively flow across the membrane, contributing to the resting membrane potential. The selectivity of ionic channels is determined by their structure, which include a narrow pore that only allows specific ions to pass through. This selectivity is crucial for maintaining ion gradients across the membrane, which are essential for cellular functions like structure. First one is structure. In the structure, ionic channels are typically composed of multiple subunits that form a pore through which ion can flow. The arrangement of these subunits creates a selective barrier, allowing specific ions to pass while excluding others. The size and charge of the pore determine which ion can move through. Next one is function. These channels are essential for variety and cellular process like action potential, muscles contraction, signal transduction. First, discuss about action potential. In neurons, voltage-gated sodium channels open in response to depolarized, allowing Na plus ions to rush into the cell, which is a key step in the generation of action potentials. Next, we will discuss about muscles contraction. In the muscle contraction, calcium channels in muscles allows Ca2 plus ions to enter, triggering muscles contraction. Next, we will discuss signal transduction. In the signal transduction, ligand-gated channels play a role in neurotransmitter signaling by allowing ions to flow into the cell upon ligand binding, influencing cellular responses. Third one, we will discuss the regulation. In the regulation, ion channels can be regulated by various factors including phosphorylations, calcium levels, membrane potassium. In phosphorylations, the addition of phosphate group can alter channel activity. In calcium level, intracellular calcium can modulate the activity of certain channels. Membrane potential. In membrane potential, changes in the electrically state of the membrane can open or close voltage gated channels. Next, pathophysiology. In pathophysiology, dysfunction in ionic channels can lead to various diseases known as channel pathologies. Examples include like epilepsy, cardiac arrhythmias, cystic fibrosis. In epilepsy, abnormal sodium channel function can lead to rescue neuron firing. Next, in cardiac arrhythmias, mutations in potassium channels can disrupt heart rhythms. Next, in cystic fibrosis. In cystic fibrosis, defective chloride channels affect fluid transport